All right. Good afternoon, everyone. My name is Prithvi. I'm a software engineer at Netflix. I'm here with my colleague, Taranga, and today we'll be talking about an interesting topic for the next 45-50 minutes, and the layout of the presentation is going to be something on the lines of we'll be talking about the architecture of the deployment patterns that we have, and then we'll be talking about the failure domains and how we guard against some of these failure domains. And we'll also dig a little deep into some of the real-time incidents that we have seen in production and how we went about triaging and debugging those. Without any further delay, let's get into the business. How many of you here use Netflix? All right, that's good to know. For the next 45 minutes, we'll see what happens behind the scenes of Netflix. Netflix is it is powered by hundreds of microservices, and data stores is like one of the key components of that. The focus of today's presentation will be on how data stores themselves are deployed on AWS. These are like some of the data stores that we use. This is not a complete list by any means, but this list is showing data stores which are deployed at scale. When I say a scale, we are talking about like tens of thousands of server instances of each of these. You probably have heard of Cassandra. You probably have heard of CockroachDB. Cassandra is a popular distributed NoSQL database. CockroachDB is also distributed, but it is primarily used for transactions. EVCache and Dynamite are something that are purpose-built within Netflix. EVCache is something that is built on top of Memcached to make Memcached distributed. Dynamite is built on top of Redis to make Redis distributed. So for the next half an hour or so, we want to actually limit or focus our discussion just on one data store, because we really want to cover the depth instead of covering the breadth. So we'll just pick one data store, which is EVCache. We'll be talking about how it is deployed on AWS, and whatever design patterns or like whatever architectural patterns that we're going to demonstrate, those are more or less applicable to any of the data stores that you can think of. So I'll hand over the presentation to my colleague here.
Thanks, Prithvi. Hello, everyone. I'm Taranga Gamatige. I'm a senior software engineer at Netflix. Here's our agenda. To set the context, we'll start with a high-level view of the EVCache architecture and its workloads. Then we dive into the details, the core part of the presentation, where we talk about different systems, tools, and automations that we have in place to operate this system at scale with very high availability. The goal of the EVCache is to provide a seamless and efficient distributed cache or key value store that can operate at scale, so our product teams and storytellers can focus on entertaining the world. So what's the EVCache? EVCache is a distributed, sharded, and replicated cache or key value store that is based on Memcached. It is replicated within a region across multiple data centers, as well as across multiple regions. We'll talk about this aspect more in subsequent slides. At the scale that we operate, failures are not rare. So we have built this system to withstand many different categories of failures, which we'll go into greater depth in future slides. EVCache client components that are used by microservices to access our clusters. This EVCache client is topology aware. That means it knows which cluster to connect to provide the best performance or fail over to other clusters when there's a network or server failure. We can add more capacity, more nodes, and we can increase the throughput and performance of EVCache. However, we want to make the cost function sublinear. EVCache can be upgraded, scaled out, while serving live traffic with zero downtime. At Netflix, we run two variants of EVCache. The standard EVCache based on Memcached, the standard Memcached that has both data and metadata in memory. Other version of Memcached, we have hot data set and metadata in memory and data on local disk, local NVMEs. Having full data set in memory is cost prohibitive for hundreds of terabytes or petabyte size clusters. That's why we use the second variant. So this is a summary of EVCache footprint at Netflix. We operate on 3 AWS regions, and EVCache is running on all these 3 AWS regions. There are about 4 engineers working, building, and operating this system. But there were many great engineers came before us, worked on this system, building it reliable and scalable. We have about 160 clusters running tens of thousands of servers. As we operate globally, we replicate data from one data center to other data centers. So we do about 15 million replications per second. EVCache clusters altogether across these regions serve more than 350 million requests per second, over 1.4 trillion items, totaling up to about 14 petabytes of data. So we can do all of this without a nosebleed, and we'll show you how. So next we'll talk about the high-level architecture. This is a very simple view of EVCache. Microservices or applications uses EVCache client library. That's topology aware. And EVCache server is a bunch of nodes that are running on like cluster of nodes. Each EVCache server node has Memcached as its core component and Sidecar as its control plane. This is a better view of EVCache cluster in a particular region. This is a cluster in US West 2. You can see that the cluster is deployed in three availability zones in US West 2, A, B, and C. Each availability zone has a full copy of data, and each availability zone that you can see, there are 3 nodes. That means the key space is sharded and spread across multiple nodes. In this way, we can add more capacity, more nodes, and increase the throughput. We use consistent hashing to shard and spread data across nodes. These replicas that we have, usually we have 3 replicas, as that's shown in this slide, but you can have configured number of replicas. The goal here is that client applications running on a particular AC, they know which cluster to connect to get the maximum read performance. They usually connect to their local availability zone cluster to serve reads. The writes are going to all replicas. Basically, writes are going in parallel to all replicas across availability zones. So that was within a region. Not always, for some of the clusters that are critical for streaming, we replicate data across regions. We do it asynchronously, so it's not in the main write path. We use Kafka as the main source for replication, and we use SQS as the backup route for cross-region replication. So in this picture that you can see, 2 regions replicating to each other, and we have 3 regions. So these 3 regions are asynchronously replicate data from to each other regions. So how EVCache is used? Let's say that you open the Netflix app, select your profile, and go to your home page. Your home page is not only unique to you, but it's ever-changing based on your viewing history and your other activities, as well as the new content that is continuously coming to Netflix. So we have about 60 to 90 seconds to get your attention, so you would start streaming something. And within that 60 to 90 seconds, we want to render home page within a matter of like few seconds and serve subsequent requests within a matter of sub-second, so you can spend more time choosing the content that you want to stream. So such a home page request on the left side making handful of calls to our API gateway layer that is spanning to hundreds of calls to backend microservices. And these calls ended up in some kind of a data store. On the rightmost leaf nodes are data stores. Out of these data stores, 80% are EVCache clusters, different EVCache clusters. So EVCache is playing a critical role for your viewing experience. It's serving these requests in a matter of fraction of a millisecond. So we have different use cases that are using EVCache. Look-aside cache is a main use case that are there to prevent read workloads from overwhelming our persistent data stores like Cassandra. EVCache is also used as a pre-configured data store. So batch processes loading data into EVCache. So online applications can read data very fast. Another use case of EVCache is for algorithms. They use EVCache to load hundreds of terabytes or petabytes of data, so they can run the algorithms in a matter of minutes instead of days, as they would if they have to use any other data store. To talk about these different workloads, I'll hand over the presentation to Prithvi.
Thanks, Taranga. That slide about EVCache footprint is my favorite. Whenever you're building any data store or deploying any data store, right, one of the key things is to have an observability aspect into it. Like, what are your workload characteristics looking like? And whatever started or whatever solution that you began with may not really hold true a year down the lane. So it's always a good idea to characterize your workloads and sort of put them in different buckets, because one solution that you have come up with may not really solve the problem for varied kind of workloads. So what you're looking on your screen here is the number of requests that are made, that are served by EVCache globally. And at any given second, the EVCache clusters are serving close to 300 million requests globally. And the different dotted lines or different colored lines that you're seeing on your screen, they correspond to the requests that are served by each individual region, which are in the range of 100 million. And Taranga also mentioned that we operate two variants of Memcached. One of them is all data and metadata is residing in memory. The other variant is metadata is in memory, and hot data is also in memory, but the cold data resides on the disk. So out of the 160 clusters that we have, about 45% of them make use of the on-disk variant, and the other 55% use RAM-based Memcached. So how do we pick and choose which use cases should use which variant and why, right? So this is, again, an interesting slide. On the left-hand side, we have essentially listed the clusters based on the requests per second that are being served by those clusters. And they are in the order of several millions per second. And on the right-hand side, for the same set of clusters, we are looking at the payload sizes that they correspond to. If you look at those numbers, the payload sizes are in the order of less than 500 bytes. So this actually helps us understand that if the payload sizes are small and if the RPS is high, it's a good idea for that data to be residing in memory most of the time. And this will also help us provision the clusters accordingly, like in helping us pick and choose what kind of instance type I should go to satisfy the network bandwidth and all of that. So this slide is an inverse of what we saw earlier. So now on the left-hand side, we are actually sorting the clusters based on the payload sizes. And if you, I apologize, the numbers are too small, but I know that they're in the order of a few megabytes. And on the right-hand side, we are again looking at the corresponding requests per second that these clusters are serving, and they are in the order of 100,000s, right? So for these clusters, it may not really make sense for us to put the data in memory because it could quickly eat up your RAM, and it could turn out to be very expensive once you start deploying these in just a RAM-based variant. All right, next to talk about observability, I'll hand it over to Taranga.
You could imagine how difficult it to navigate when you're blindfolded. This is how it will be if you're trying to operate a system in production, especially a mission-critical system, without observability. If you have to pick one tool to operate a critical system like this, that should be your observability tools. These tools are your eyes and ears into the system, very critical to run a production system at this scale. So we have different observability tools in place. We collect metrics. These are on top of the metrics that are provided by AWS, by the way. We collect metrics from client side. We collect metrics from server side, and everything in between. We also have a system where we can configure and see the dashboards on different components of the system. It's not only metric collections and dashboards. We also have an alerting system that can notify us when things are about to go bad, so we can proactively take measures and fix problems. Our metric system is based on Atlas, which is an open source system, and we extensively use eBPF tools, again, for both troubleshooting and monitoring. Let's look at some examples. This is a dashboard of read latency of clients. We measure read latency at 95th or 99th percentile, because that is what meaningfully turning to your user experience. For example, how long it takes to render your home page. Here's another dashboard. This is server network usage. Depending on the EC2 instance type that you pick, you have different network characteristics. It has different bandwidth limitations, different PPS, packets per second limitations. Memcached is so efficient. We are always bottlenecked by the network. So we monitor network very carefully to make sure that we are not overwhelming the network, because if network is overwhelmed, it's going to start dropping packets, and requests going to delay or time out. Monitoring clients and network is not enough, because we have to monitor Memcached as well, because that's a core piece of our system. And we also monitor Memcached in different tangents. Here, a dashboard that shows how many free pages Memcached has to allocate for new data. In that way that we know if free pages are falling below a particular threshold, we can proactively scale out clusters before it starts evicting data. Therefore, it's very important to understand workload characteristics and then size our clusters accordingly. I'll let Pruthi talk about how we reason about resource usage of Memcached.
Thanks, Takana. All right, so how do we provision any solution on AWS, right? So it's always a good idea to know what kind of application you're dealing with. Is your application compute bound, is it network bound, or is it memory bound? For the purpose of, again, this discussion, I won't be covering everything, but I'll just focus on the caching tier, since we are talking about EVCache here, and I'll jump right into the memory aspect of it. So for folks who have used Memcached, for folks who have not heard of Memcached, at the crux of it is a hash table pointing to a bunch of doubly linked lists. So, and that allows us for insanely fast lookup of order of 1. And what this command here is doing is it's taking 2 parameters. The first one corresponds to -m 27,000. It corresponds to the amount of memory that is carved out for the items, storing the items itself. And hash power corresponds to the size of hash table that you want to maintain. So just by looking at this command, we can gauge, or we can understand how much memory we need to provision for Memcached process itself. But there is a lot more bookkeeping that goes behind the scenes when you deploy your Memcached server instance, right? So Memcached also would need memory for maintaining its connection objects. It would also need memory for its read response buffers, where it would need to copy data from its sockets, and again, copy the data back to the kernel buffers, and so on and so forth. So how do we carve out the total RAM that you have for Memcached itself? So that's a $1 million question, right? So if you provision too less, you're not making efficient use of your RAM. At the same time, if you give too much memory to Memcached, you're leaving little to no resources for your kernel to operate with, and it can lead to lot of bad things, like daemon can come in and it could come and kill any random user space process. So in this particular example, 2.27 corresponds to 128. The fact that this instance or this machine can hold up to 128 million items with an average data size of 220 bytes. But in reality, this is not how production workloads work. There could be few items which could go into the order of like several kilobytes. There are few which could consume like very little memory. So you need to have a good idea about your workload, and only then you'll be able to provision your clusters effectively. And general rule of the thumb that we have identified, or we have sort of found out after operating these many clusters over these many years, was try to make sure that the total memory that is consumed by Memcached, including the memory overhead that comes from the connection objects and buffers, it is scoped under 90%. All right, what happens in the day in the life of EVCache, right? So Taranga mentioned that we can operate all of this without a nosebleed. I would say 90% of that is true, but 10% of the times we do some level of firefighting. But the fact that 90% of the time we can get a good night's sleep is because we have like really good systems in place to do the auto remediation most of the time. So we'll be talking in this section about different failure domains and what are the systems and tools that we have built in place to safeguard ourselves. So what are some of the bad things that can happen, right? Your instances can crash. AWS Health Check routinely recycles its hardware. Memcached process itself could get terminated because there could be a buggy code path which gets executed, and Memcached process can get killed. Disks can go bad because remember we use a disk variant of Memcached, so disks can go bad, and the data that is residing on the disk itself can get wiped out. So what do we do in situations like that? So we have a system that is built which will automatically take care of repopulating or rehydrating data on the lost instance, and we call this system as instance warmer. And let's take a concrete example to see how that happens in action. So here we are looking at US East region. For the sake of this discussion, I'm just taking two availability zones, 1C and 1D. And in each of these availability zones, we have 3 instances, and 3 instances each. And this cluster is healthy, so reads and writes are served by both the replicas. So let's say in replica 2 or in US East 1D, one of the instance has gone down. So a brand new instance comes up in its place with empty data. So we have a high-level orchestrator or control plane that constantly monitors the health of these clusters. And when it detects the fact that one of the instance has gone down, it will identify a healthy replica, and it will start instructing those clusters to start dumping the data so that instance 3 in a replica 2 can get rehydrated. So it will trigger this workflow called as dump the cache contents, and the contents of the cache, they get uploaded to either EBS or S3. We'll get into the details of why EBS, why S3 in the later slides. But for the moment, just know that the data gets moved to some persistent store. And once the data is uploaded to EBS or S3, there is another microservice called as cache populator, which reads this data from EBS and S3, and it will start writing to the brand new instance that came up. So while all of this is happening, the reads can be served by the other healthy replica. It's just that the clients or the apps will see a momentary increase in the latency because they're retrying on multiple replicas for a given request. Right? So what we saw just now was just one instance going down, but there are other situations that can happen, like workload changes can happen. So we have Christmas holidays right around the corner, and that's a very popular time for families to get together and start watching a nice Christmas movie, right? And we do expect on the back end that there will be a surge in the traffic, and we have to make sure that our clusters are scaled well to handle that kind of incoming load. So how do we scale out on a week's notice or probably a day's notice? So we have another system built in place that's called as cache warmer, which will move like petabytes of data in a matter of hours, and we'll see that in action in the next few slides. And these are like some other common reasons why we would have to scale out. So there could be like some critical Memcached upgrades that came in, or there could be a Intel Spectre kind of a meltdown, Spectre meltdown kind of an issue that can happen. So we might be forced to upgrade our operating system. Or there could be few instance types that AWS decides to deprecate, and we are forced to move out of a particular instance family. There could be like different reasons, but we should be prepared regardless on how we can scale out faster. So this is the high-level architecture or the block diagram that shows different components of what does cache warming really entail. We already saw what is cache warmer controller. That's like a orchestrator or the brains behind this entire workflow. Then on the bottom side, you see EVCache existing, which is the cluster that is serving the live or production traffic. And the new EVCache clusters are just empty clusters that are sized according to the new needs that we have. And on the left-hand side, we have the standard Amazon SQS and S3 services. So let's see what happens when a cache warming activity happens, right? So the moment we start scaling out a particular cluster, we create a dedicated queue for that particular warming event, and then we instruct, or rather the controller instructs the sidecar or the control process that is present on the EVCache server machines to say, start dumping and uploading your data to S3. And the data gets uploaded to a particular S3 bucket, and the location of that S3 bucket is added as a message to the queue that we just created. And in the meantime, the controller also instructs cache populator, which is more like a consumer of these messages, to start reading the uploaded chunk information from the Amazon queue. And once cache populator reads this data, it can write to one or more replicas. And all of this happens in an automated fashion without any human intervention. And on any given day, we are talking about at least like tens of clusters getting scaled out on a regular basis. So I said hold off your question about why we use S3 and EBS. So the reason is mentioned on this slide. So if you look at the previous slide and this slide, everything looks the same, except the fact that the SQS and S3 services are replaced with EBS. So the previous architecture actually worked fine for several years, but as the scale has increased like multifold, S3 was not really cutting it out for us. The reason is S3's traffic and the live traffic, both of them will go through your instances Ethernet NIC. So they both are contending with each other. And sometimes we have noticed it when the cache warming activity was happening, the latencies on the app sides have increased. So since then, we started to look at other alternatives on how we could work around this. And EBS, Amazon EBS has rolled out a feature, I believe early 2020 or late 2019, where they could allow attaching the same EBS volume to multiple instances. So we thought, okay, how about we leverage this, because EBS comes with its own network. It doesn't take the instances network bandwidth. So we don't impact the production traffic. So we started experimenting with it, and then we rolled out into production, and it proved out to be extremely fast, and at the same time, it was not impacting the live traffic. So the workflow is very similar to the previous architecture, where we provision EBS volumes, and we make sure they get attached to the existing EVCache cluster and also the cache populator cluster, because the existing cluster is more like a producer and cache populator is more like a consumer of the data. So we instruct the data to be dumped. The data gets uploaded to EBS. On the cache populator side, it will start reading the data from the EBS volume now, and the new data chunks get returned to the EVCache. There is also another important component that got updated that you're seeing on the screen, which is called as a native cache dumper. So if you look at the previous slide, that was grayed out. The biggest change was in the previous architecture that was completely based out of Java. And we noticed that there were several limitations when we want to really push the data at a faster pace with Java-based applications. So we decided to rewrite that entire application in C++. And it's open sourced as well. And the link to the blog post is given below.
So some of the EVCache clusters are used as like data stores that I mentioned before. The backend batch jobs push data, and the online applications reading data from the stores. Sometimes there are bugs in these applications that could corrupt data that is loaded to EVCache. So in such situations, the traffic get disturbed because they cannot read the correct data from the EVCache. So to safeguard EVCache from such corruptions, we have implemented a backup feature where it snapshots caches at certain times. So if there's a corrupted data set, you can go back in time and restore an older data set. So there are other failures that if you are running your services on AWS or any computing platform for that matter, there are other failures that are common in such distributed systems at that scale. Data centers, the availability zones could fail. There could be correlated failures in a data center, maybe the bad hardware or due to like noisy neighbor. And regions could fail altogether. If you can recall, there was a region outage in 2012, the Christmas Eve. The Netflix was out of service for hours due to the region outage. Since then, Netflix moved into a global model where it's not operate in an island model anymore. So EVCache is also designed to move along with that, the global model. So whatever the failure is, instance fails, data center fails, or region fails, EVCache can serve traffic from another availability zone or from another region altogether. So in this slide that you can see in the zone A, an instance fails. Since EVCache client is topology aware, now EVCache client can serve those reads from other zones, other replicas, while instance form automatically kicks from the background and refills data to the failed instance. Similarly, if a region itself fails, then we can seamlessly move traffic to other regions. Since EVCache data is replicated to other regions, EVCache can seamlessly serve requests from other regions. It's not only regions can fail, they will fail, and when it happens, EVCache is ready to serve, continues to serve the traffic. To make sure that our systems are resilient for region failovers. We exercise such failovers very frequently. Probably you have heard about chaos engineering. Chaos monkey, probably most of you have heard about, killing instances. Chaos Kong is the exercise that we do to forcefully evacuate regions. So Netflix is ready for region failovers. So this is the last section that we're talking about, a different set of problems. So far it sounds great. We have systems, tools, fallbacks, automations, everything in place so we can handle all of these failures without any problem. In reality, it's not that rainbows and unicorns. All of that can be handled maybe like 90%, as Prithvi mentioned, but there are certain issues that could arise, specific issues that could arise in cloud environments that you have to be ready of. So we pick a few incidents to talk about. The goal of this section is to a couple of things. Tell you that expect the unexpected, and when that happens, be ready with a deep system knowledge and a good grasp of Linux observability tools so you can quickly troubleshoot and recover from such errors. For this section, we pick up 3 incidents, a P95, 95th percentile latency issue we troubleshooted, a client issue, and some memory issues that we triaged. There was an application with 95th latency of 5 milliseconds, and as you could see in this graph, the latency was way above the 5 millisecond SLO. So this particular cluster was running the disk-based Memcached, but we expect deterministic performance from the disk, basically sub-millisecond latency from local NVMEs. So we can hide the disk latency behind the network latency, and client application would not see much of a difference when Memcached is reading from memory or disk. Well, in practice, that's the case, but in theory, that's the case, but in practice, there could be many factors come into play, especially if the disk bandwidth is overwhelmed, we don't get the deterministic latency that we expect. So that was the case in this particular scenario. So few things to look at is whether your online traffic is contending with any other traffics. So in this case, the online read traffic was contending with compaction and write traffic. Another thing to look at is whether your workloads are spiky. If your read peaks and write peaks overlap with each other, and if you cannot do anything, then you have to scale your clusters to match that load. If you can work with application teams and offset these peaks, then you can save some resources. So both workloads can go in at different times without overwhelming the disk. In this particular example, we first delayed the compaction by changing the configuration. That relieved a little bit of disk bandwidth, but it was not sufficient to get the latency down to like 5 millisecond mark. So we have to go to a different EC2 instance type and scale out the cluster. We use BIO latency and BIO Snoop. These were like really great eBPF tools that you can use to troubleshoot such issues. Another issue that we troubleshoot is EVCache client was used in a containerized environment, and it was running out of its ports to connect with the server side. So this is a very interesting failure. Server is healthy, network is healthy, but if client application cannot connect with servers, from client application's point of view, server is not available. Our standard tools did not help to get us most details into why it's exhausting ports. We knew that it's running on MISOS agents, and MISOS agents are running with like 1024 limited number of ports, but there's no way that we could exhaust those ports. So we looked into MISOS, and we found out it's using Linux network namespaces. So we use IP tool to identify what are the namespaces that are running on this box, and then looking at the JVMs and identify which JVM is using which namespace, and then use socket stats to identify what are the ports that particular JVM is opening to the server side and why it's leaving, exhausting all the ports. And then we realized it had gone to a failure path where it's opening but not closing connections properly. So in the TCP state machines, that many ports were left alone in the closed wait state, which means it has received the FIN from the other side, but operating system is waiting for application to close this port. Application is leaving for JVM to garbage collect it. Works most of the time when the failures are rare, but when failures are frequent and happening back to back, it is exhausting available ports. So we have to fix the problem by patching the client. So it will aggressively close the ports without waiting for garbage collector to come and garbage collect this. This is an example of like a problem, a bug that is been hidden but surfaced by some combination of other failures. These things would happen and can happen, and when these things happens, like we need to make sure we cannot step back and say, hey, this failure should not happen. Rather, like we should make sure that our components are resilient for such failures. To talk more about the memory issues, I'll hand over the presentation back to Prithvi.
Thanks, Ganga. All right. For folks who have opened and looked at kernel log messages, maybe something like this is familiar to most of you. And what we are looking on the screen is basically a page allocation failure for order 4, which corresponds to 64 KB memory allocation that basically failed. Right. So let me give you some context on why we are talking about this. So we saw that we use EBS for cache forming. So for the vast majority of our fleet, everything was working fine, but there was like this one particular cluster where some of the EBS volumes, the AWS console itself was saying the volume is attached, but when you go on, look on the instance itself, you don't see that volume appear, and the details are in the kernel logs, and the reason why that failed was the block driver would need a 64 KB allocation to happen, and that didn't go through, so that device never came to be seen. So that effectively rendered the entire workflow in a failure state. So what can then we started like digging more into why did this happen in first place, right? So on this instance, we started looking at the state of the memory. Okay, and this is a standard command, a Linux command free. Most of you are probably aware of it. That is showing it has about close to 31 GB memory available, and most of it is used. And the next one that we wanted to look at is look at the proc buddy info that is available in the proc file, procfs. And the bottommost line that if you read through it, you can see that the normal zone has about 100 MB memory, but the higher order pages starting from 4 and above, everything is 0. So this is basically telling us the system is heavily fragmented, and that was the reason why the previous allocation failed in first place. Then we started going little deep into this, right? Like why, who is consuming this much amount of memory? If you look at if you remember the slide where I talked about what is the ideal amount of memory that you want to give to Memcached, we said try to aim for about 90%, right? So that was not actually happening on this particular machine when we started looking at the top memory contenders. And if you look at the Memcached itself, that was taking up 95% of the total RAM that we have on this instance. So then we actually dig a little more into where these memory allocations are happening within Memcached, and we saw a code path in Memcached where it was allocating memory in an unbounded fashion, which led for it to just consume it was just hogging memory like anything. And since then, we worked with the open source Memcached community to come up with a patch, and we were able to fix this issue. So the point of these slides is when you run into any issues, it could be your native application memory leaks that could surface as problems while attaching an EBS volume, which are totally unrelated, right? So you could be triaging or debugging issues in a tangent manner. So it's always a good idea to have a good methodical way of slicing and dicing and narrowing down the issues and then debug it. The other set of issues that we saw with memory-related things was we are talking about Memcached user space, memory consumption, all of that, which is fantastic. But there are few other memory horrors that are not always visible. For example, Memcached can be operated on TCP or UDP. We use the TCP variant. And whenever Memcached, for whatever reason, gets slow, all the packets that are arriving and sitting in your TCP sockets, it could just keep waiting and it could blow up the TCP memory usage. And there were a handful of clusters which almost bothered us for several quarters, where the instances were randomly getting killed and we couldn't identify what was the reason this was happening. And we switched gears and we started inspecting the TCP buffers, which could be monitored by using SS command or sockstats. Sockstats gives a nice cumulative output, whereas SS command just dumps at the per socket level. And we noticed that the default TCP memory limits were quite high. They could technically eat up your entire RAM. So based on our application and based on our usage, we decided to actually limit the TCP memory by working around with some of the sysctl parameters that are there. So whenever there is, essentially the application is slow or there is a sudden spike in traffic, your TCP buffers could go up. So if your application is, again, tied to TCP, this is something that we can pay attention to. So a few other things when it comes to memory-related issues is see if there is a sudden surge in the queries per second or reads per second on your clusters, and see if you're throttled on the read-write network on your particular instance, and also observe the memory that is consumed by the kernel. It need not be just TCP, but it could be other file system buffers, which could be contending with your user space processes from time to time. All right, with that, we are almost at the end of the presentation. So what are the takeaways, right? We want to present you with the architectural patterns that we have used to operate these data stores on AWS. Know your use cases and workloads better. Only then you'll be able to come up with effective solutions that really fit your needs. Invest in observability from day one, because if you can't observe, you can't really optimize or iterate on top of it. And continuously improve on reliability and scalability. So you can start with a solution, you can observe how it is behaving in production, take the feedback from it, then optimize and iterate on it. It is a continuous journey. Operating data stores is not like a destination that we reach, but rather a journey that we all have to take. All right, with that, we are at the end of the presentation. Thank you, folks, for your time. So we have about 10 minutes for taking questions. So looks like we don't have a mic, but if somebody, go ahead. I'll just repeat it for the audience. Yes. Yes.
You knew that that was your baseline. And then when you observed that it was using around 95%.
Correct. That's true. That's true. Yeah. So the question is, how did you arrive at the baseline of 90%? It's definitely driven by data more than anything to arrive at that sweet spot. Because no, I would say it is applicable across the fleet. It's not specific to any particular use case.
The important part there is like we need to make sure that we are accounting for resources in a very tightly manner. So if there's a surge of traffic or anything, we will gracefully push back and give a degraded performance instead of server-side nodes are crashing. So that's why we are trying to account and preserve resources like memory, CPU, everything in a very tight manner. So server-side would not crash when there's a surge in traffic.
Yeah.
How is topology information communicated to clients when there's a failure? Is that failure propagated to other clients? And when you scale up horizontally, how do you prevent resharding of your items to different nodes?
Okay, so two questions. The first one is the discoverability and the topology aware. What was the second question?
Reshard.
Okay. Okay. So the first question I can take, and the second question you can go ahead, Taranga. So for the first one, we use this discovery service called Eureka, and that is responsible for all the clients essentially rely on Eureka for the discovery information to get the topology. So that is how they effectively manage that.
Yeah, when the particular node crashes, or if a particular node doesn't have data, it connects to the node and try to read the data. If it cannot read the data, or if it cannot connect to that particular node in that replica, it automatically fails over to another node in a different replica. For the question about the resharding, let's say that we have 3 nodes cluster and we want to scale out to 5 nodes. We do not increase the number of nodes in the source cluster. Rather, we stand up another cluster side by side with 5 nodes and let the writes go into the new cluster, but only writes, and start the replica warmer in the background that will move data from old cluster to new cluster. And when the new cluster is ready, new cluster will start serving both reads and writes, and old cluster will be toned down later. So what will happen is, when the replica warmer goes on, it doesn't do a set, it does add. So if a particular key is added by the real-time traffic to the new cluster, the replica warmer would not add that key. So that way otherwise we'll run into the problem that you mentioned. If you increase the number of nodes, and now the keys would rehash to different nodes, and there will be misses.
Yeah, also that will help with not having any stale data as well, because you're not adding.
That's a question over there.
So you mentioned that you have the entire cache in its entirety in each of the availabilities, right?
Yeah, the full data set, yeah.
That means that you are essentially writing to each of the availabilities on a parallel, like you said. How do you avoid data leaks when you get these?
You want to take it?
Repeat the question.
So actually, let me take that. Let me repeat the question, and one of us can answer. So the question is, since the same write is getting replicated to multiple zones at the same time, how do you make sure that the data remains consistent across replicas? That is the question.
Yeah. So to make it, so you're talking about a scenario where the same key is being written by 2 different clients concurrently. Is that the scenario that you're talking
same
about?
client. Yeah.
Yeah. Yeah.
Correct. Yeah. Yeah.
So we have a couple of mechanisms. We have a mechanism, a configurable quorum that application can use to say, hey, wait until all writes succeeds or majority of writes succeeds. Obviously, we don't want to have all, because there will be nodes that are failing, and if you do that, we will be seeing more write failures than you want to. So we have background system that can detect these write failures and go into that particular replica and remove the stale value from that particular node.
You have a side
Exactly. So if you say like, hey, try to 3 nodes, one fails, application will see a success, but we notify that to the offline process asynchronously, and that goes ahead to that stale value and remove that value from that one. There's a
I'll
question behind your, yeah. Oh, sorry.
Go ahead, go ahead. So yeah. So the question is, we rely on components like cache populator, the orchestrator, and for doing cache forming activity. Those components themselves can fail. So how do you get protected against that? So that's a really good question. So I would say these are not like long-running things. When we say cache forming, we're talking about bringing up the system, using it for few hours and tearing it down, as opposed to having those things running for a longer amount of time. So there are situations when some failures can happen, but I would say the incidents are really rare because again, you're competing with time, right? Having an issue, seeing an issue in a matter of 1 hour versus seeing an issue in a matter of a month, I would probably bet on a month because that system is up for 1 month, whereas this is just up for like few hours. So that's where my I would say the failures can happen, but it is like really scoped down.
Yeah, also, we have made all this component in the cache form workflow resumable and restartable.
Yeah.
For example, dumper fails, dumper knows where it failed, like start dumping data. It will resume from that place and start dumping data. If populator fails, the SQS message goes back to the queue. So a new populator comes up, get the message, and start downloading data from S3 and warming. So all these the different failures are restartable as well as resumable.
Yeah, so the cache controller itself, as I said, has the notion of what's happening. So if something were to go down on the dumper side or the populator side, it can actually autocorrect things. Yeah. Can you repeat the question? Yes, we do checkpoint. For doing the checkpoint itself. So what we do is for every data chunk that we upload, we also compute checksum of that file. So we know what file that we're working on at any given point in time. And since, if you remember the S3 SQS story, we are actually relying on SQS or the queue to really help us navigate how far are we in the process. If a particular message is pulled from queue, we know that that data is already consumed, right? Yeah. Yeah, go ahead. So just time check, we have 2 minutes. Okay, let me repeat the question. So if there is a AZ level failure or if there is a region failure, how do you ensure that the remaining availability zones or the remaining replicas in other regions can withstand or take on that surge in traffic? So Taranga, you want to go ahead?
Yeah. So AC failures are rare, but AC failures, mostly what we see is degraded performance on certain ACs. So when the traffic when moved to other replicas, the traffic is not moving to one replica, rather split between other 2 replicas. So not a particular replica get overwhelmed. So when we are provisioning, we also keep a space for the failovers. Within a region, if a particular AC fails, then the traffic to that particular AC is split and send it to other 2 replicas. Now, we also provision our clusters for region failovers. If a US East 1 is evacuated, that traffic again get like split into EU West 1 and US West 2. So those clusters are again scaled to handle those like failover traffics. So our clusters are basically provisioned for the failover peaks.
So just to add on to that, so we have 3 regions, right? So we have like 33%, 33%, 33% requests that are getting served. So if a region goes down and one of it, the 33 divided by 2, it's roughly 16%, right? It gets redirected to the other 2, and we make sure that we have left that much capacity. And the way how we figure out from time to time is we do this something called as Kong exercises, chaos Kong exercises routinely to simulate region failures. Yes, we do actually simulate them, yes, in production, yeah.
So the question is whether the chaos engineering happenings in the production, it's absolutely the case. Chaos monkey is the famous one that goes and kills the node. At our scale, we don't need chaos monkey because we have so many nodes, and nodes are getting terminated very frequently, so we don't have chaos monkey. But chaos Kong is a larger version of chaos monkey, which evacuates a region altogether, and that is happening in the production. So we don't. So the question is, the chaos Kong is chaos monkey is happening all the time. There's no notion of the low peak or high peak. Chaos Kong, we don't do chaos Kong during like holidays, right?
Yeah.
But on other times, we do not purposely pick a valley, but we pick a normal time of the day because that would be more realistic to simulate region failovers. Question?
So the question is, do you have hotkey issues and how do you deal with it? I would say yes, absolutely. We do have some hotkey issues, and remember I mentioned that we use Ketama hashing, and Ketama hashing is a consistent hashing scheme, and there is internally it uses something called as virtual buckets, and you can always increase the spread of virtual buckets to make sure that your data again gets resharded and the distribution gets better. Again, it all goes by use case by use case. There is no single point answer to your question, but resharding the data by increasing the number of virtual buckets is definitely one way to avoid that issue.
We also do the key hashing. So we allow like different hashing schemes. So we get like even spread of keys across the nodes by hashing the keys itself before finding out which node it has to go to. But still, you can have hot nodes. So what we do is in that place is gracefully degrading the performance. Basically, if some application is bombarding a particular node, that application will get pushed back. So that application will see more timeouts, not other applications.
Yeah, we got a time up signage, so we'll just step down, and if someone has more things to chat about, we'll be happy to hang around for some more time.
Thank you very much.
Thank you.